Okay, hello everyone. So we have two more invited talks. So the first talk is by Professor Etienne Brasselet from University of Bordeaux, and he will present on spin orbit model shaping of vortex beams. And okay, so let us know more about the speaker from Andre.
Hello, Etienne Brasselet is a research director at CNRS, Laboratoire Ondes Matière, Aquitaine, Université de Bordeaux, France. His scientific interests cover wave-matter interactions in the framework of multidisciplinary environment, including nonlinear phenomena, optics and photonics, acoustics, mechanical effects of waves, solid and soft matter systems. Research activities mainly focus on situations where structured fields meet structured matter, which makes topology and vector fields at play in various circumstances.
Okay, thank you very much. So let us welcome our speaker to give his talk.
Thank you. So first, thanks Vijay and Ravin for the organization, smooth organization of this lecture for me to come here and sharing with you very specific aspects of how material processing can be used to manipulate light. So from the program, I saw that this morning some folks were dealing with light manipulation using nano and micro advanced manufacturing. Here I will present a very specific aspects of it in the framework of what is called vortex beams. And in order to have everyone on the same page, I will first introduce what are those electromagnetic structures that I will deal with in a visible domain, but the exposed techniques and strategies can be easily extended to invisible light, whatever the range of it. I mean, regarding the blue part or the infrared part. So what do we mean by optical vortex beam? Actually, these are beam of light that contain optical phase singularities. So this implies that we define these objects, the optical phase singularities. It corresponds, let's say at first mathematically, as points in space where the phase is undefined. And this is the wording of optical vortices. As you can see here, there are two examples. These are the two simplest, robust points you can find in waves, which are the singularities. As if you see my mouse pointer here, at this point, all the color of the phase meets, but they meet in a different manner. On the left part, they meet in a clockwise manner, and on the right part, they meet in a counterclockwise manner. This means that here we deal with two generic optical vortices which are constitutively distinct. And if I let the time moving on, what do we see? That the phase pattern of those structures is rotating with time. And this means that this oppositely rotating time-varying phase, or spatially oppositely rotating phase in space, could be associated with a distinct characteristic. And this characteristic is the topological charge. This is a quantity associated with the circulation of the phase around a closed path contour encircling the phase singularity. So on the left side, we will deal with the topological charge -1, which means there is a -2 pi coverage over a full turn around the origin, and the sign is positive on the right part here. Optical vortices actually are what I call here the norm, in the sense that these are very natural manifestation of light, although their structure is relatively, I would say, non-common in the sense that they are non-smooth structures. to exemplify this, I just took here, I shoot a set of random plane waves, a couple of them, tens of them, in a random manner. The phase and intensity are represented here, right and left patterns. And actually, there is no need for specific preparation in order to observe in the field here a collection of plus minus one topological charges. And those phase singularities at the place where they are, since the phase is undefined, there is a natural consequences. The consequence is that the intensity is not defined at those points. Here you can appreciate this where in a central panel where I saturated the intensity represented on the left part of the screen. So this 0 point associated with singularity actually are of many uses in several kind of applications. I won't review here due to the time constraints. However, I would like to mention that if you construct a beam that carries an optical phase singularity, then you will deal with an optical vortex beam. And here represented with the two situations we presented just before, topological charge -1 and +1, and in the middle, the typical Gaussian beam. Those beams are associated with an orbital angular momentum per photon, meaning that the optical current is circulating around the beam propagation direction. And this confers a very interesting property for the light beam, which are vortex beams. And all the more interesting is that these properties, which are generically restricted to topological charge ±1, can be extended mathematically to any charge number L, running from -infinity to +infinity, which extend the application ranges, at least the day we were able to control them. Because those structures with high topological charge are inherently unstable to perturbations. The question, when you want to deal with them and to use them for technologies, the idea is how to fabricate them. So to have a better understanding of which kind of technology could be used to fabricate them, it's interesting to understand from where they come from the very basic equation of electromagnetism. I mean by that, the Maxwell's equation. In fact, a very simplistic identification of them can be obtained in a paraxial approximation relating to wave with a scalar approximation. When you combine this, you have what is called the paraxial Helmholtz equation, which is a scalar equation, partial differential equation, that you can solve mathematically exactly, which means that any paraxial field can be described by a superposition of modes, and the family of those modes actually can differ depending on your decision. I would say, for instance, the geometrical basis you will use. A prototypical example is using cylindrical coordinate system for which Lagrange beams, Lagrange modes are a very representative kind of elements to describe vortex beams, because every of the modal components actually is proportional to this term, which actually is representative of an optical phase singularity with topological charge L, where L is an integer. Here are the family with the first modes regarding the two indices involved. The azimuthal one we just described before, associated with the phase singularity, and the one P associated with the radial distribution of the amplitude. And in order to master them, the idea is to fabricate them from scratch using a Gaussian beam. And for that, in the very early days of beam shaping towards the generation of optical vortices, holography was at work actually. And I give here two examples of early days binary amplitude holograms that were used to generate optical vortices. Here you can see it was simply a plastic printed with ink and beam passing through them, and the diffraction from them is providing an optical vortex beam whose interference pattern is shown here. So those results dates back 30 years ago, which was I would say the very early day of holography, singular optics holography. Of course, the kind of holograms of singular hologram could be of different form. Here it was fork. It could be spiraling holograms, and similarly, the diffracted beam will be an optical vortex beam, as you can appreciate here, even if the quality at that time of the picture were not that good. An annular profile whose interference pattern shows the involvement of additional fringes, signing the topological charge 1 in the present case. Nowadays, holography can be developed and extended to any kind of patterns. And here there is an example, which is a result coming from a result made with some of my colleagues who will talk tomorrow, Professor Malinauskas and Jotkazis. And you can appreciate the scale. This can be done at very small scale using nanofabrication techniques of different kinds. Here it was simply a focused ion beam etching. In order to have those beams on demand and in a way that it is flexible to play with, the aim is of the community dealing with the generation and use of optical vortex beams is to have agile solutions that enables not only the generation of optical vortex beam of various kinds and their superposition, but also the capability to them on demand, both in space and in time. So for that, some technologies, and one of them is develop holographic reconfigurable optical elements, which are the generic class of special light modulators, which could be of amplitude type or phase type. Size, typically it's 1 megapixel, as the usual, I would say that's the standard. And every pixel enables the control locally, independently of phase. These are two examples: a digital micromirror device where the beam is deflected on demand from one pixel to another, or liquid crystal special light modulator where the phase is, in that case, modulated from one pixel to another in an independent manner via electrical control. So these kinds of elements are not only useful to produce what we call structured light in a very broad sense, but also to analyze them. And the analysis of light, of structured light, of singular fields is actually of great importance, because actually the kind of example I was showing before were non-modal, and this is the point of what I want to discuss. The point is that helical phase masks associated with the generation of optical vortices actually do not produce Lagargos beams from Gaussian beams. This is a meridional view of a Gaussian beam incident on the helical phase masks here in magenta color, propagating from left to right. As you can see here, the shape here is propagation varying, which means that the mode is, there is not a mode here. There is a superposition of modes with different radial structures, with different P. So the L index is well defined, but the P index is not defined at all. Actually, it's an infinite superposition of P modes. So you are not dealing with a well-defined information regarding the L and P modes, which means in terms of the basis of an element of a basis describing the global field. In a far field, it is still the case, even though it looks like this is a donut profile. Donut profile, elegant one, does not give the LG10 mode. It is the same and even more pronounced for higher order topological charges. And because of that, we realize that complex modulation is required, and not only the helical phase profile imparted to an incidence field. And this is why we started 5 years ago to propose a new way to assess optical vortex generation with the modal characteristic using the spin-orbit interaction. The idea is to go back to the effect of the half wave plate in a circular polarization states, which flips the handedness from right to left or left to right as light passes through. It happens that if you look closely to the expression of how a circular polarization or circular polarized light is transformed by the half wave plate, you realize that there are two phases at work. One related with the average refractive index of the plate, and one related to the orientation of the plate. This phase is a geometric phase. And by controlling the geometric phase, which is related with the coupling between space and polarization degrees of freedom, you can control the phase, as is the case when you are traveling and you are experiencing jet lag. And the idea is simply, if you want to deal with optical vortices, you simply need to shape azimutally the geometric phase, so the orientation of your alveolus plate. And then you will have a geometric spiral phase plate. Consequently, you will obtain spin-controlled optical vortices. However, these are non-model spin-orbit optical elements because these are helical phase masks, although they are spin-controlled. It's not enough. And for that, to solve this problem, what we propose is to detune the plate from the alveolus plate condition. And in that case, the output field emerging from a generic plate with an arbitrary retardance delta, which is pi for alveolus plate, gives you these two terms where we recognize here the geometric phase and here the dynamic phase. And the idea is in two steps. We can see that the phase of the Lagergos phase is already here. You just need to shape the orientation psi of the optical axis properly. And by shaping the retardance of the plate, you can shape the Lagergos amplitude on demand. And now, if you project on the appropriately polarized circular component, then you will get your Lagergos mode simply with an appropriate shaping of orientation of your birefringence and its strengths. Regarding the P modes, you simply need to take this into account via the appropriate additional shaping here, plus minus pi, in order to get sign control. And here is the demonstration, the experimental realization using nanostructured glass and comparing the standard and the model beam shapers, which are shown here to summarize the situation, where this is a regular vortex shaper, which is not propagation invariant profile. It's not a mode. And here, when you are dealing with a model shaper with appropriately tuned birefringence. To get even better situation, you need to realize that dynamic phase actually is spoiling your beam. Actually, there is not full propagation invariance. And the point is to realize that while you are managing by advanced manufacturing, this laser processing, the retardance, you are at the same time modulating the refractive index, hence the dynamical phase, and this spoils your masks. So the idea is to get benefit from the geometric phase itself, which remains an degree of freedom, and to encode the correction that will cancel the drawback of the radially modulated retardance to compensate the unwanted dynamical phase component. And here is the results, which will conclude my presentation, that we did very recently using dielectric metasurfaces made of silicon nitride, with a colleague from Shenzhen University in China. And the idea was simply to control the nano building blocks in order to correct the geometric phase on demand with respect to the need. And here is a demonstration where the standard metasurface here exhibits the shape, the non-invariant shape of the beam as light propagates from left to right. And here is with the geometric phase correction. And if you are not using the appropriate spins, you are not recovering the modes as you are expecting. And this spin asymmetry will be tackled in a future work. So I stop here. I'll be happy to answer a few questions if you have some. Thank you for your attention.
Yeah, thank you very much, Professor Etienne, for the wonderful presentation, insightful presentation, I would say. And so now let us see if we have questions from the audience. So is there any questions? Okay, so I have a question related to your final slide on using metasurfaces to obtain this vortex beam. So can you please, comment on the efficiency of these metasurfaces as compared to, conventional devices?
Yes. So here. So in general, as soon as you want to deal with modality, you need to project, as shown here. Which means that even though your element, when the condition is set to half-wave condition, is fully efficient, which is the case, shaping the amplitude implies to accept an amount of loss. Because the idea is to sculpt the Lagrange profile from a Gaussian profile, an incident Gaussian profile. So by construction, it's not a redistribution of the incident field into a vortex. It's a one-step shaping of the amplitude and the phase. So the drawback is loss of forward power, I would say, that fits the desired mode LP. In practice, we are dealing with several tens of percent of global efficiency. Typically, it's like depend on the indices you want to reach. Typically, it's several tens of percent.
Okay, thank you very much. And I have a follow-up question on this. So you have selected, this type of antenna. So I think there are different types of antenna, like C-type antenna, cross-type antenna.
Sure.
So how to find the optimal, antenna for this device?
So I would say this will depend on the tools you have access to and on the capabilities of your tool. Because typically, different kinds of antenna will provide you with similar, I would say, if they were ideally fabricated, they will provide you with a similar optical response. So it's a compromise between two things, between the simulation, because when you are preparing your nano mass, what you are doing, you are proceeding first to simulation to know what would be the optimal design for that. For if you want a parallelepiped, as here, what is the appropriate dimensions? Those dimensions, as you can see here, in fabrication, they are rounded. So you are targeting an ideal situation. You are fabricating a real parallelepiped, which is no longer a mathematical parallelepiped. And then if you want to have a full control, in general, it will be two steps. You first make an ideal design, you realized it, and then you can post-correct at the second round of fabrication in order that the rounded antenna, if they are designed to be sharp, behaves properly. So I would say that it's a matter of sometimes a matter of taste, but often a matter of local expertise regarding a given tool you are using. But
Okay.
there is no,
thank you very much.
There is no, I would say, generic claim stating that a parallelepiped is better than a C, for instance. It just depends on what you want to do and how you can achieve it.
Okay. Yeah. Thank you very much. And okay, so there is a, question from Prof. Vidas.
If I can, Etienne, as a follow-up of a previous answer, have you at least rough estimation of how this accuracy in the produced structure correlates to the result? Is it linear or non-linear? Let's say from the rectangular you have, I don't know, as shown here, maybe 10% variation. Will it correspond to 10% deviation, or will be it amplified, or vice versa diminished? Perhaps it's case dependent, but still interesting to know how in this fabrication inaccuracies are resulting into the modeled result.
Okay. So I would say I know only one study where it has been evaluated, but not in the sense of optimizing, just in the sense of to see whether it is compromising the expectations. And the results was, let's say, order of several percents, I would say. So let's say below 10% drawback. As you can see here from the date of this reported work, which is just last year, a couple of months ago, and these results here, where you can see that the meridional cross-section of the beam propagation from left to right here implies that we have some imperfections. So clearly, even before optimizing the building blocks themselves, there is also other things that should be improved. For instance, the zonal design here. Here it's a concentric design, a piecewise design that was chosen for the first demonstration. But the first point would be to make this continuous. So I would say there are first design improvements to be reported. To change the material would be good as well, to explore other techniques, which we are doing with several collaborators, among which yourself. And so I would say we'll learn with more work which manufacturing option is better for this spin orbit route to optical modality, which is very important in my opinion for optical information processing and communications.
Okay, thank you. And it opens another field where perhaps microscopy and deep learning can be employed to optimize the model based on the feedback of what it produces.
Exactly, how to make it cleverly, I would say badly fabricated, but perfectly operating.
Yeah. Thank you.
Welcome.
Okay, so thank you very much. And let us see if there are any further questions. Okay, so no further questions. And so let us thank the speaker once again for the nice presentation. Thank you very much, Professor Etienne.
You're welcome.